VA and B dash belongs to VB such that A dash A is equal to B dash B and A dash is equal to BB dash. Correct. So these are the three parts. Basically, second part is the dual of first part, and first and second together imply basically if third part is followed by first second, because if AB belongs to H, then it means what? AB belongs to L and R, because H is what? L intersection R. So AB belongs to L and AB belongs to R. So if AB belongs to L, this side is true, this side is true. If AB belongs to L, this side is, by first this is true, and by second this is true. And if you talk about the converse, so if A dash A is equal to B dash B, then AB belongs to L, and if A dash is equal to BB dash B, then second AB belongs to R. So third will be followed if we do first and second. And second is dual of first, means similarly we can do for the second also, isn't it? So basically we have to do just only first part. See the first part. AB belongs to L. A comma B belongs to L. It is given first because converse part is trivial. That is, when A dash A is equal to B dash B, it's simple, isn't it? Why it's simple? We will discuss later. First, try to understand this. It means that is LA is equal to LB, because A and B are related to each other. So LA is equal to LB. So try to draw egg box picture. This is A and this is B. LA is equal to LB. Correct? This is RA and this is RB. Now, since A and B are regular elements, so their inverses exist. At least one inverse exists, A dash B dash. Correct. So we know that. So if A dash belongs to VA, then A dash A is idempotent in LA is equal to LB. Correct? Why? Because we know that, you know that well, A dash A, these are related to each other. As we know that A equal to A dash, in previous lecture I wrote four identities, two identities. A equal to, we know that A equal to what? A equal to A dash A, and A dash is equal to A dash A dash. If A dash is the inverse of A, then it is true. And so from this A dash A LA, isn't it? And LA is equal to LB. So A dash A is, so A dash A belongs to LA basically. So A dash A, we know that it is idempotent. So A dash A is idempotent in LA as well as LB. Correct? So it has it is where it should be. Where it should be? It should be here, A dash A, because A dash A is related to related to A and it is related to B, so it should be here. So here it is idempotent, correct? Now, as we know that every class contains at least one idempotent, so assume the R class RB contains the R class RB. The R class RB contains at least one idempotent, say E, by, so RB, for example, if it contains idempotent like here, E, so it is LE, correct? Say E, by proposition 2.3.2. So now you see two idempotents are at the cross point, E A dash A, E A dash A. So by theorem 2.3.4, there must exist the inverse of B dash here at the diagonal position, isn't it? B dash. Then by theorem 2.3.4 second, also write here by proposition, by same proposition in which it is given that the R class contains at least one idempotent, you write in the bracket here. So then by proposition 2.3.4 second, the H class, which H class? This H class, that is R A dash A intersection LE. The H class R and the H class R A dash A intersection LE contains an inverse B dash of B such that B dash B is equal to what? A dash A, such that B dash B is equal to A dash A, correct? And BB dash is E. B dash B is equal to A dash A and BB dash is equal to E. So in this way we have proved that B dash B is equal to A dash A, correct? Now see the converse part. If there exists A dash belongs to VA and B dash belongs to VB such that A dash A is equal to B dash B, then A and B are related to each other. This is trivial. How? You see A dash A is equal to B dash B. You know that A dash A is related to each other. It is related to A and this is related to B. So by transitivity A and B are related to each other. So second converse part is trivial. So second, all of you can do in a similar way, all of you can do by yourself, and third is followed by first and second. If first, second are true, then third will be true, because if A and B are isolated, then A and B must belongs to A also and must belongs to R also. So in this way, this theorem is proved. Now I would like to tell one thing, that if you talk about the regular semigroup, S is regular semigroup. Now we take a regular semigroup, correct? Now you see, if A is regular, you take any element A in S, then there exists some X in S such that A can be written as AXA, isn't it? So it belongs to ASA. You can say it belongs to AS, for example, because XA is a member of S, so we can say that A belongs to AS. So when A belongs to AS, it means what? We need not to take like this, basically A belongs to AS. Also you can write A belongs to AXA. You can say that A belongs to SA. Also you can say A equal to AXA, it belongs to ASA, isn't it? So we can drop all references to S1, isn't it? We simply say that ALB if and only if SA is equal to SB. ARB implies AS is equal to BS. AHAJB implies SAS is equal to SBS. We need not to write S1, isn't it? We just write S. Why? Because because A belongs to AS, A belongs to SA, A belongs to ASA, isn't it? For example, if you write S1A, S1A is what? SA union A, it is so, isn't it? We take S as a monite, isn't it? It means it contains an identity. We are taking S1 as like this, S union 1, isn't it? So if if we take simple SA, so it is not necessary that A belongs to SA, not necessary, isn't it? It may be possible that A does not belong to SA, but if S is regular, then A, we have shown that A belongs to SA, A belongs to SA, A belongs to SA. Otherwise, it is not guaranteed that A belongs to AS, isn't it? A belongs to SA, A belongs to SA. It is not guaranteed until unless semigroup is a semigroup is a monite. Semigroup is identity. But if semigroup is regular, then A belongs to AS, A belongs to SA, A belongs to SA. So we just write like we drop this S1. We can just say ALB if and only if SA is equal to SB, ARB if and only if AS is equal to BS, AJB is if and only if SS is equal to SBS. Right? So basically, first notice that if S is regular, then A belongs to AS, SA, ASS. Hence, in describing the green equivalences for a regular semigroup, we can drop all references to S1, and we can say simply that if A, B are related, then SA equal to SB, ARB, AS is equal to BS, and AJB is equal to SA is equal to SBS. One thing is this. Now, if you are taking use a sub-semigroup of S, correct? Now we are taking only U to be regular, for example. U is sub-semigroup of S, and this is semigroup, and we take a regular sub-semigroup of S, correct? Isn't it? So if you use the sub-semigroup of S, and if we take U as a regular semigroup, then we will prove some result. Proposition 2.42. Before that, I like to tell one thing is that, for example, if we generally use a sub-semigroup of S and S is a semigroup of S, then you don't take U to be regular. First, I would like to tell that is AB belongs to LU. LU. LU is what? It implies there exists UV in U1 such that UA is equal to B and VB is equal to A, because we have to take here U1 because we are not taking U as a regular semigroup. So when A and B are related to each other and A and B LS, it means that there exists ST in S1 such that SA is equal to B and TB is equal to A. Basically, we want to differentiate between U and S. That here semigroup is U, here semigroup is S, and well, U and S are connected in such a way that U is a sub-semigroup of S. So when A and B are related to each other, we know from the definition. A and B are LS related to each other, we know the definition, isn't it? Also, remember this, LAU, this is the class of LA class. So it is U belongs to U such that A comma U belongs to LU, correct? If you talk about LAS, then it is what? S belongs to S such that A comma S belongs to LS, correct? Now, there are some facts, trivial facts, that LU is contained in LS intersection U cross U. Similarly, RU is contained in RS intersection U cross U. HU is contained in HS intersection U cross U. DU is contained in DS intersection U cross U. JU is contained in JS intersection U cross U. All of you can do by yourself. It's very easy. Correct? So similarly, we can write this for R, U, S, R. Similarly, we can write for next annihilation, that is R, H, D, J. It is true for R, H, D, J. Same thing is true. Correct? Now, one fact is that if S is infinite cyclic group generated by A and U is infinite monogenic sub-semigroup of S, this is cyclic group, correct? And U is what? Infinite monogenic sub-semigroup of S. U is infinite, S is infinite cyclic group generated by A, and U is infinite monogenic semigroup sub-semigroup of S, consisting of all powers of A, consisting of all positive powers of A. Then LU is equal to RU is equal to HU is equal to DU is equal to JU is equal to 1U, correct? And LS intersection U cross U is equal to RS intersection U cross U, same HS intersection U cross U, DS intersection U cross U, JS intersection U cross U is equal to what? U cross U. So I left this as an all of you have to do by yourself, isn't it? Try to do by yourself. It is easy. Now finally I will do the last result of today's lecture is proposition 2.4.2. Proposition 2.4.2. If U is a regular sub-semigroup of S, then LU is equal to LS intersection U cross U RU is equal to RS intersection U cross U, and HU is equal to HS intersection U cross U. So I will do this. Second one is dual of this, and third one is the consequence, because if these are true, you take the intersection, isn't it? These two implies directly this, because HU is what?